We are now recording. Class is officially in session. Okay, well, this is the last time that we're going to see each other. Actually, I should probably rephrase that. This is the last time that you're going to see me. Last time I saw you guys was 2 months ago. But yeah, this is the last time we're going to get together as a class. Oh, I'm so sad. So the plan for today is that we're going to spend the whole hour going over the practice test. I hope we can get all done in an hour. We will not be meeting on Friday, but there is going to be a quiz today, and today's quiz will be due on Friday. My policy all along has been that I give you 2 days to take the test, unless it's a week, and then I give you 3. So I think it's reasonable that you take today's quiz by Friday. It'll be an easy one. Okay, so no class on Friday, and then Monday, I won't be online or anything. I will have the test posted just like we've done before, so you guys know how it works. Everybody has to take the test at the same time, and it'll come in 2 parts. Part 1 will be multiple choice, just like it was last time, and part 2 will appear as a separate assignment, but you have to do both of them. And part 2 is a free response where you do the work on paper and take a photograph and upload it just like we did last time. Okay, so I see Jaren is asking if I'll count your test submission late. Yeah, Jaren, I will. You're talking about the practice test, I presume. But yeah, I mean, late is late. If Canvas tells me that it's late, then it'll be late. But I mean, this is the last assignment, right? So if you got any late passes at all, no problem. You'll still get full credit. Now, if you've used up all your late passes, okay, then that's a problem. Okay, so make sure that you talk to your parents and siblings to give you exclusive access to the computer next Monday between 1 and 3. Make sure that you have a camera, a digital camera, so that after you do the work on the paper, you can then take a photograph of the work and upload it to Canvas. Okay, and then also return your books after the test on Monday. You're gonna need them for the test on Monday, but after the test is over, then return the books. Okay, so before we go in the practice test, let's go over the quiz questions last time. So for the wormhole, all of the questions, or all of the answers that you saw there were correct. Pretty straightforward, I think. The surface of our planet has positive curvature, and the way that we define positive or negative curvature is take whatever surface you've been given, be it a globe or a saddle, or think of it in terms of a convex lens or a concave lens, right? So if you were to draw a triangle on the surface there, then add up the angles of that triangle. If the angles add up to 180 degrees, then it's a flat surface. If the angles add up to some number greater than 180 degrees, then we say that it has positive curvature. And if it's less than 180 degrees, then we say it's negative curvature. Okay, all right. So question number 3. The name of the principle that says that a new theory has to give the same results as the old one if it's applied under conditions where the old one works. Okay, that one was called the correspondence principle. Now, the names that they've chosen, correspondence principle and equivalence principle, are potentially confusing because if 2 things correspond to each other, doesn't that mean those 2 things are kind of equivalent to each other? So I can absolutely understand why people get confused about this. I wish scientists have chosen different names, but they didn't. So I write it down on your cheat sheet. So what you see here, this is the correspondence principle. And the equivalence principle is the one that says that accelerated motion is equivalent to gravity. Okay, question number 4. There is no experiment that you can do without cheating. So like I said here, if you were to drill a hole in the wall, okay, admittedly, that experiment would probably answer the question for you. But there's a probability that you might not be alive to see the answer to the question because there might be the vacuum of empty space on the other side of the wall. Okay, so there's that one. And then finally, there was only one answer to this one. So if you got this one wrong, I don't know how you did it. Okay, so before I get into the practice test, just a reminder, don't forget there will be a quiz today. It'll be an easy one, and it will be due on Friday. Okay, so let's get into the practice test. Let me switch over to a different screen here. That would be this one. Okay, and oops, I should have positioned that up at the top there. Okay, so what you see here is the test, and so I've got the answers written in red. So the reference information that you see here, I will give you the exact same reference information on both parts of the real test on Monday. So up at the very top of the test, you'll see these numbers here. So you don't need to have this on your cheat sheet, although it wouldn't be a bad idea to have it on your cheat sheet. But all this information will be there. Okay, so question number one, we want to derive E equals mc squared. So I hope you guys agree that deriving E equals mc squared is actually one of the easiest, if not the easiest derivation we did all year. Okay, you just need to know where to start. So the equation for energy of a photon as a function of frequency, that's E equals hf. Okay, the equation for the wavelength of a particle as a function of mass and velocity, okay, that was lambda equals h over mv. And these are things that were experimentally determined. Okay, so we can't really sit down and theoretically say, you know, this is what the theory says it should be. This is just a statement of what has been observed to be true. Okay, so then all we have to do is a little bit of algebra. We just have to take each one of them and solve them for h. And then when we do that, we put the two of them together. So we got E over F is equal to lambda times mv. And then we multiply both sides by F. And then we replace F with C over lambda. And then do a little more algebra. And then we recognize that if the energy is an electromagnetic wave, then the V is going to be equal to C. And so bingo, we got E equals mc squared. Okay, so some of you are arguing that maybe the impulse derivation was easier. Yeah, maybe. Yeah, it could be. All right, so I hope this one is easy and straightforward. Okay, so next, I want the three predictions of special relativity. So you need to have very clear in your mind what's the difference between special relativity and general relativity. So I hope you guys all do. So special relativity is the weirdness that happens when you're moving at high speed. Okay, so here they are. So time dilation, in other words, time runs slower for clocks that are moving. Not just clocks, for anything. I mean, for living objects. Anything that you can think of to measure time, whether it be the aging of your body or how fast your brain processes thoughts or the ticking of a clock, anything that can be used to define what does the word time mean, it's going to happen more slowly if you're moving. Okay, length contraction. Okay, they shrink when they're moving. And make sure you understand, it doesn't shrink in all directions. If I've got a ball, that ball doesn't shrink in all directions. It only shrinks in the direction of motion. So if it's moving horizontally, that ball gets squished like this. It's the same height. It's just the dimension that's aligned with the direction of motion. Okay, that's the one that gets shrunk. And then mass increase. So, you know, an object at rest, you pick it up and you start it moving, you've given it energy that increases its mass. Okay, so the trick is to know whether to multiply by gamma or divide by gamma. We're going to talk more about that later. But in all three cases, gamma is the factor that you need to either multiply or divide by. Okay, so now the 7 predictions of general relativity. Well, here they are. So mass energy equivalence, gravitational time dilation, gravitational lensing, the red and blue shift. And now a lot of people say black holes as a separate entity, but actually black holes are just a special case of gravitational redshift. So I don't list black holes separately. Gravitational waves, gravitational frame dragging, and precession of orbital paths. All of these are things that we've talked about before, so I don't want to take the time to talk about them now. If you don't know what any of these are, go back and watch the recording. We spent a lot of time and it's all recorded. So Josh wants to know if we have to call them by names or if you can simply describe them. Yeah, probably, as long as you describe it well, I'd let you go. And also, if all you do is call it by its name, but you don't also put at least a couple words of description, I won't give you full credit. You need both the name and the description as well. Or if you want, as Josh just asked, if all you did was the description, I guess I would accept that, but make sure you include all 7 of them. Okay, so the experiment that scientists did that first proved the light is actually a photon and not a classical wave. All right, so that was the photoelectric effect. And so we talked a lot about that in class. I don't think that I need to spend the time going over it now. What you see written here pretty well describes it. So let me just super briefly just summarize it. So scientists were working with photoelectric cells, solar cells. They were shining light on the metal and they were measuring the energy of the electrons that were ejected. And we call that the stopping potential. And I trust if you don't remember how that works, go back and watch it. Basically, you take a parallel plate capacitor and you do it in reverse. Okay, so you measure the energy of the electrons that are emitted. And so when they increased the intensity of the light, they were increasing the amplitude of the light, and they found that the energy of the ejected electrons did not increase, which it should have. I mean, if it had been a traditional classical wave, increasing the intensity would increase the amplitude, which means that those electrons should have had more energy, but they didn't. Now, it is true that you did get more electrons. Okay, so conservation of energy was not violated. You did get more electrons. But the electrons should have had more energy, and they didn't. And this was a huge problem. And it wasn't until Einstein came along and suggested his theory about electrons being photons, little wave bundles. That was the only time that it finally got accepted. So Ellie is asking if I'm putting the answer sheet on Canvas. I don't even need to bother asking. If I ask you whether you guys want that, I know I'm going to get a flood of yeses. So, okay, I will do that. After the class is over, I'll put it on Canvas. Okay, so the experiment that scientists did, which proves that solid matter is not little particles, little marbles like we thought it was, but it's actually waves, just like photons. Okay, so that was Louis de Broglie's experiment with electrons where he shot them through diffraction gratings. And now he had to shoot them through really small diffraction gratings, because if he used the same diffraction gratings that Thomas Young had used for his experiments with light, the electrons would not have shown a diffraction pattern. They would have just gone right through there. And the reason is because the electrons have wavelengths that are way, way, way shorter than light. So in order for Louis de Broglie to get his effect here, he had to actually take a crystal and shave it really thin and shoot electrons through the crystal. So Yasmin wants to know if you could just say Thomas Young, but smaller. No, I would like a little more detail on that. Okay, number 6, the correspondence principle. Well, we just talked about that one, the answer to the quiz. So I'm going to skip over that. Okay, so the wavelength of a proton moving at a speed of such and such. Okay, so you need to know the equation. So right here, lambda equals h over mv. That's the equation everybody needs to know. Okay, by now you should have used that equation so many times that you've got it memorized. So let's just plug and chug, it's all you need to do. So when I do the numbers, I get 6.89 times 10 to the negative 11 meters. Okay. Now keep in mind, this is a proton now. So we've done so much work with electrons that, sometimes we need to remind ourselves that electrons are not the only objects in the universe that have waves. Protons do too. Yeah, Josh is making that mistake. Yep, that's when I first wrote the question here, I had it as an electron, and then I said to myself, no, I'd better change it. And so, yeah, it's the mass of the proton is given in the reference information up at the top here. Okay, next one, the longest wavelength of light that can cause an electron to be emitted. Okay, so in this case, you need to know that the work function is just equal to the energy of the electron that just barely has enough energy to kick the electrons free. Now, when the electron, so if the electron has just exactly that amount of energy and no more, then it'll kick the electron free, but when the electron comes out, it won't have any kinetic energy. Okay, so so all you have to do is just find out what's the energy of this electron or of this photon. So just do E equals HF, and out pops the answer. But remember, if you're using E equals HF, the answer is going to come out in joules. Okay, which for part A is exactly what you want. Now for part B, okay, then we have to take our answer here and convert it to electron volts. But converting from joules to electron volts should be no more difficult than converting from centimeters to meters. Well, in the one case, just move the decimal over. Okay, so I'll admit maybe that's a little bit easier. But yeah, it's just conversion, and you guys should know what the conversion factor is. Okay, question number 9 is really important. Basically, now I didn't use the word Heisenberg uncertainty principle here, or I didn't use the phrase Heisenberg uncertainty principle because I didn't want to, give it away. But basically, that's what I'm asking. Is in question number 9, I'm asking explain the Heisenberg uncertainty principle. Okay, but I purposely didn't call it that. All right. Well, the answer is that matter is not made up of little balls like everybody thought it was prior to Louis de Broglie coming along. Okay, matter is actually a wave, and that wave looks like what you see over here. It's got a couple wiggles in it, and then it approaches zero, but it approaches zero asymptotically, which means that it never really reaches zero. It just gets really, 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 really close to zero. Okay, so, and then the second part that you need to know is that if you take a probe and you stick a probe in here, you cannot know where that probe is going to go ding. Okay, all you can do is calculate the probability that the probe is going to go ding. So if you're in the middle of the wave function here, you have the highest probability, but it is by no means certain that that probe's going to go ding. That probe could go ding anywhere along here. Okay, so if somebody asks you, where is this piece of matter? Your answer has to be that it's impossible to say exactly where it is. So all you can do is ask them, say, what level of certainty do you want? Do you want 90% certainty? Do you want 95% certainty? You want 99% certainty? Because depending on what level of certainty they want, that determines how big you're going to draw the box. And the box is designed so that if you sweep the probe everywhere inside that box, then there is a 95% probability, or 99, or whatever number you chose, then that somewhere in that box that probe's going to go ding, but it's never 100%. Okay, so the size of the box is determined by the wavelength, because the number of little wave peaks that you see here, that's a fixed amount, but the wavelength varies according to the equation lambda equals h over mv. So if an object has less momentum, that means the wave is going to be more spread out, and therefore the uncertainty as to where that piece of matter is located becomes greater. Okay. All right, so I hope that this makes sense. I think I described it pretty well in my thing here, and I expect that you guys to be able to describe it equally well. Okay, number 10. All right, so I don't want you to see the answer to number 11 just yet. Okay, so number 10, we're saying that special relativity, we're going to temporarily pretend like we don't need to worry about it. And we're going to say, okay, if we've got this parallel plate capacitor, how much voltage do we need to get that electron moving at 90% the speed of light? Okay, now, what I've seen in the past is that a lot of students don't know where to start, because a lot of students have forgotten what we did a couple months ago with parallel plates and electrons. Okay, remember the electron gun. In fact, maybe I'll even draw a picture here. Let me draw again. Okay, so here's the parallel plate. Here's the other one with a hole in it. So here's the electron. We shoot it out there. Okay, and the thing that a lot of students forget is the definition of voltage. So the difference in voltage between that plate is defined as, okay, the work that is done divided by the charge. Okay, so if we want to know how much energy this electron has, well, we know that energy is going to be equal to the amount of work that's done. Okay, so if we just multiply both sides, then we get work, which is equal to the kinetic energy. That's is going to equal Q times V. And the kinetic energy is 1/2 mv squared. Now this V here, this is a little v. This V over here is a capital V. Don't get that confused. So little v is for velocity. Capital V is voltage. So 1/2 mv squared equals Q times capital V. So if you don't remember that, then you have no hope of doing this problem. So make sure you understand that. Okay, so we start right here with this equation, and then all we do is just plug in m, because we know the mass of the electron, and I know that the velocity is 90% the speed of light. Now here you're going to have to actually put it in meters per second, so you can't just leave it as 0.9c. You're going to have to put in the number. But when you do this, here's the answer that you get. Okay. Okay. So Jaren used the more precise speed of light and got 206. And yeah, good for you, Jaren. That I probably should have done the same thing. Yeah. So good for you. Okay. Now, okay. So now in problem number 11, I said, okay, let's go back and redo that problem, but this time let's recognize that special relativity really is a thing that needs to be worried about. And so this equation, let me go back up here and let me turn on annotation again. Okay, so this equation up here needs to be modified because of special relativity. M is not going to be just M anymore. The faster that thing moves, the more mass it has. So we have to replace M with M over gamma, where gamma is, of course, 1 over V squared minus C squared. Okay. All right. But that's pretty simple. Just do that. And then again, you don't really even have to do any algebra here. I mean, other than dividing by Q. Okay, so after you divide by Q to get V here, then just plug and chug, and you get an answer that's more than twice as much as what our previous answer had been. Okay, more than twice. So you can see that special relativity is very definitely a thing that you need to worry about if you're moving at speeds that are anywhere near to the speed of light. Okay. So yeah, Jaron, okay. Oh, so 206 versus 207. Okay, let's not worry about that. Yeah, don't worry about that. If you can show me you know the physics, I'm not going to worry too much about rounding. So Yasin is asking, did I just divide by gamma? Yeah, that's all I did. That's all you need to do. Okay, all right. So, oops, I forgot I'm still in annotation mode here. Let me get rid of annotation mode. Okay, so how much energy does a photon have if it's got a wavelength of such and such? Well, this is exactly the same question up above, a couple pages earlier, where we were asking about the work function. It's the exact same equations here. If we just know the energy of the electron, then we know the work function. Somebody's playing around by drawing on my screen, huh? Okay, well I am going to, okay, I just made it so you can't draw on my screen anymore. Shame on you. Okay, all right, so number 12, I think is pretty straightforward. Just remember, whenever you use equals HF, your answer is going to come out in electron volts. Or I'm sorry, the answer is going to come out in joules. And if you want it in electron volts, you know how to convert. Okay, so Jaren, don't worry about it, okay? Let's just move on. All right, Jaren, if you want, I'll be glad to talk to you one-on-one after the class is over, and we'll figure out what went wrong. But for now, let's just move on. Okay, so question number 13. So now this is the first question that I think is really very difficult. Up until now, I would hope that you guys agree those are all pretty easy. But even this one isn't really that hard. I mean, okay, so we know what the work function is, and we know what the wavelength of the incoming light is, so we want to know what the kinetic energy of the photoelectrons is going to be. And we call them photoelectrons just because that means they're the electrons that are emitted when the photon hits. Okay. All right, so the key here to understanding this is to understand that the incoming photon has a certain amount of energy. Some of that energy is going to get used up in breaking the electron free, and we call that the work function. And whatever energy is left over, that's how much energy the electron is going to have. Okay. Now, the trick about this problem is the units. So I gave you the work function in electron volts because that's the way it's usually done. Okay. And so if you take E equals HF, or E equals hc over lambda, which is the same thing, okay, that is going to come out in joules. And you can't mix the two. You got to decide, are you going to work in electron volts or are you going to work in joules? You can't go mixing them. All right, so what I've done here for part A is I converted from electron volts to joules. And so now I know how many joules the work function is. Okay, so then I can do hc over lambda to tell me how much energy the photon had. Subtract out the work function, and whatever left over, that is how much. That's how many joules of energy these electrons are going to have. Okay, and then in order to convert that back into electron volts, I know the conversion factor, so that's pretty easy. Now, this problem could have been solved more easily if we had worked in electron volts. And so just for grins here, I included that one as well. If we had started from the very beginning, okay, we could have used the book's equation. In fact, let me turn on annotation again. Okay, so remember this equation here that a lot of you asked me, where the heck did that come from and why would we want to use it? Well, here's a case where it's really easy to use. Okay, if we take that equation, we know that if we plug in lambda, we plug in the number of nanometers, okay, not with the 10 to the negative 9, just the number of nanometers, okay? And then when we do that, so we take 1240 divided by however many nanometers it is without the 10 to the negative 9, then the number that comes out will not be in joules, it'll be in electron volts. So it's really quick and easy to figure out, okay, so the energy of the photon then is 2.92 electron volts, and the work function was given to us in electron volts. And so just subtract the two, and we get the answer in electron volts. So if part B was all I had asked for without asking for part A, this is the way I would have done it, just because it's faster. But the other way up here, this way will never let you down. And so if you want to only memorize one way, this is the way to memorize, not the other one. Okay, so let me clear all of that away. All righty. So we're up to number 14 now. Whoops, I want to put that down. I don't want you to see the answer just yet. Okay, so we know how much time passed for the person on the spaceship, and we know how fast they're going. So we know that we're either going to multiply by gamma or divide by gamma. We know it's one of those two. How do we know which one it is? Well, what we do is we look at it and we say, okay, is the time going to be more back on Earth or is it going to be less back on Earth? Okay, so we know that the person on the spaceship who's moving, it's going to be less time for them. So if what we're looking for is the time on Earth, we know that it has to be a bigger number than the number that we've been given. And we know that gamma is always a number that's less than 1. Okay, so if we multiply by gamma, is that going to give us a number that's bigger? No, it's not. It's going to give us one that's smaller. So we know that multiplying is the wrong thing to do. So we know that what we need to do is divide by gamma. And so when we divide by gamma, we get 3.3. Okay, if you look at it this way, it's really straightforward. You just logically think your way through it. Don't try to blindly memorize. Just logically think your way through it. Now, I do need to mention here, when you guys turn in the homework for special relativity, I didn't say anything at the time, I probably should have. I went in and I looked at what you guys submitted, And I was unpleasantly surprised at the number of people who multiplied by gamma when they should have divided, or divided by gamma when they should have multiplied. You know, you got a 50-50 chance of guessing it right. So it looks like almost 50% of you got it wrong. So that means that you're just guessing here. Don't guess, okay? Think your way through it. Now, those of you that got it wrong, you know, don't worry, I didn't subtract points. You guys know my policy is that the score I give you is a completeness score, not a correctness score. So even though you got it wrong, I still gave you the points. But on the test, you got to get it right. Okay, so don't blindly memorize. Think your way through it. Okay, so just for good practice, let's do the next one, and let's think our way through it using this same pattern here. Okay, so the question says we know the speed of the electron, and we know, now the question doesn't say that we know the rest mass, but we do know the rest mass. We've done so many homework problems with electrons by now. You should all have the rest mass from electron memorized. Okay, so we know the rest mass, we know how fast it's going. So the question is, to get the moving mass, do we multiply by gamma or divide by gamma? So let me just pause for a second and ask you, what do we do, guys? Do we multiply by gamma or do we divide by gamma? Okay, there we go, 50%. This is really disturbing, guys. Half of you are saying multiply and half of you are saying divide. Oh, it's just like the homework. Oh, guys. Okay, so, all right. Okay, so Victoria is giving a reason here. Okay, Victoria says because we know that the answer has to be bigger. Okay, we know that the moving object has more mass. Okay, and so if we want to get an answer that's bigger, and we know that gamma is less than 1, then we know that multiplying is the wrong thing to do. We have to divide. Okay, all right. So, so Jaren, I see you're saying that you checked the guide at the front, but what I want you to do is don't rely on the guide at the front. What I want you to do is logically ask yourself, is the moving mass greater or is the moving mass less? So just logically think your way through it. So we know that the moving mass has to be greater. So therefore we know that multiplying by gamma is the wrong thing to do. Dividing is the only way to do it. Okay, and so when we divide, we get this. All right, now question number 16 again. Let's do it again. Don't worry, Jaren, it's okay. Don't berate yourself. Okay, so question number 16. Again, I'm going to ask the same question. We know that we're either going to multiply by gamma or divide by gamma. Which one's it going to be? I want to see some answers typed into the text box here. Are we going to multiply by gamma or are we going to divide by gamma? Okay, so I see multiply, multiply. Okay, looks like everybody's agreeing that multiply is the right thing to do. Okay, and Jaren is justifying his answer. Jaren is saying it's because the objects get smaller. Okay, good. It looks like everybody's in agreement on this one, and so am I. Okay, so multiplying by gamma is the right thing to do. Take the derivative. Oh, Josh, I don't know what I'm going to do with you. Okay, question number 17. Okay, so we're supposing that a person could live on the surface of the sun, which is, I do not recommend you try it. Okay, but if you could, then we know that time is going to slow down for you because the sun has a lot of mass, right? So if you're in a high gravitational field, your body and your clock are going to feel more stress and therefore they're going to run more slowly. Okay, so I'm asking you to do the calculations. And up at the top of the page, or up at the beginning of the test, I gave you the equation. So all you have to do is just plug it into the equation, right? So here's the equation. And so if 1 year has gone by for the person in zero gravity, so I'm just going to call it 1, because as long as I use the same units on the left side as I do on the right side, I can get away with it. Okay, so for t in zero gravity, I'm just going to take a 1. Okay, and then I'm going to multiply it by this factor, which I have not derived. All I'm doing is suggesting that when scientists use this equation, they get results that match their experiment. Okay, so this is not derived, or at least I haven't derived it. Okay, all right, so I plug it in and I get a number that is got a heck of a lot of 9s in it. And then, so then I say, okay, now if I follow the rules for sig figs, okay, then I would have to round this off to 1.000, okay? And then I would have to conclude that there is no discernible difference, okay? But just for fun, let's throw out the sig fig rule. And as I say here, please don't tell Mr. Miller that I'm throwing out the sig fig rule, because he will never let me live it down if he hears that I did it. But just for grins here, okay, let's assume that all of these numbers that we're working with don't just have 4 sig figs, but let's suppose that the radius is actually 6.9600000 with as many sig figs as we want, okay, which is not true. But just for fun, let's try it, and let's see what happens, okay? So if we do this, we find out that this number of years, 0.999999 and maybe another 9, I lose track, 7878. If we convert that into seconds, we get this number here. But if we take one year exactly converted into seconds, we get this number here. And the difference between those two numbers is 67 seconds, which Milo is saying is actually 66.92. Okay, good. All right. Okay, so about a minute's worth of difference. Now, because of the sig figs, okay, we cannot say that the difference is exactly 67 because we don't have enough sig figs to do this, okay? But it's going to be somewhere on that order, right? It's going to be somewhere in that ballpark of around a minute, okay? Okay, now let's see. Jaren, I've been ignoring your question here. I suppose I should read it here. If you fall in a black hole, what would kill you first? I don't know, but either way, you'd be dead. So I don't. But so if you see any black holes, stay away from them. Okay, so now number 18. So I'm going to do this 2 different ways. Let's make sure that we understand. Okay, so we've got an electron that's been excited up to the n equals 6 level. So that means it's up in that orbital where if you were to take the circumference of that orbital, that circumference would equal 6 wavelengths. Okay, and we got it up in there, and we don't care how. I mean, there's a lot of ways we could have got it up there. We could zap it with high voltage. We could have 2 electrons bump into each other. Doesn't matter. Somehow it gets up there. So then it drops down to the n equals 4 level. So what's the wavelength of light that's going to be emitted? Okay, so what I do is I look on page 756 of the book. So I highly recommend that you guys bookmark that, because I can pretty well guarantee you're going to need that chart. Okay, so we can see what the energy levels are. So at n equals 6, we got this much energy. At n equals 4, we got this much energy. So the difference is this much. Now, those numbers are given in electron volts. Okay, so what we do then is we say, okay, well, the energy of the photon is equal to HF, or HC over lambda, is a more convenient way to write it. But if we're going to use this equation, whatever numbers we plug into that equation have to be joules, not electron volts. So we got to take this number here and we got to convert it into joules, which is easy to do. And so then we plug in Chug and we get an answer of 2,700 nanometers, which seems pretty big because up until now, we've always been dealing with wavelengths of photons that are, 400, 500, 600 nanometers, because that's the visible part of the spectrum. So this 2,700 here is clearly not in the visible part of the spectrum, it's in the infrared part. Okay. Now, there is another way we could have done this problem. And again, it's using that book's special formula, okay, where the energy is 1240 divided by the wavelength, or if you rearrange it, the wavelength then is going to be 1240 divided by the energy. Now, in this case, this is going to be more convenient because the energy is given in electron volts, okay? So if we put in the number here, the number we'll get out will be 2,700 without the times 10 to the negative 9. It'll just be 2,700. And so we need to know that that's not 2,700 meters, that's 2,700 nanometers. We just need to know it. Okay, we're moving along pretty well here. We've only got 2 problems left, but they are fun problems. Now for problem number 19, all I did was go back into the presentation that I had done to you guys a couple days ago, or maybe I guess a couple weeks. Boy, time flies. Okay, so what I did was I just took this slide right here, which I just screenshotted it right off the presentation. Okay, so let's talk about it. So we got an electron that is going around a proton, and we know that in order for this to be a stable orbit, the length of the circle, the circumference, has to be an integer number of wavelengths. If it's not an exact integer, it will not be stable, because when the front half of the wave goes around and comes and wraps over and overlaps the trailing part of the wave, if they aren't lined up exactly right, they're going to interfere destructively with each other. So it won't be stable. So this circumference has to be an integer number of wavelengths. So that means that it has to equal some n, which n is a whole number of wavelengths. So 2 pi r has to equal lambda, n lambda. Okay, so then what I did is I just substituted in for the de Broglie wavelength. We know the lambda equals h over mv, and did a little bit of algebra. And so then, and by the way, okay, we need to know this relationship over here. Remember how we got this relationship? I thought that I had included that. Oh, I got these a little bit out of order. I should have done this one first. Okay, but well, I guess it doesn't really matter. But anyway, okay. So, but had I done this one first, it would have been better. Okay, so we got an object going around another object in a circle. We know that the force that's attracting them is ma. But if you're moving in a circle, we know that a is v squared over r. Okay, and so we know that the force is Coulomb's force, which is k q1 q2 over r. Oh no, and here I've got that same typo in it. I forgot. Remember the typo that you guys corrected me about, and I forgot to get it. So where you see q squared here, remember that's not q1 squared q squared. That's a typo. Sorry about that. It's q1 q2. So down here, this one is correct. Okay, but this one up here is wrong. Okay, so tell you what, let me just, in case anybody's paying close attention. Nice. Okay, so let me X that out. Okay, sorry about that. Okay, but this down here is correct. Okay, all right, so k q squared over r squared equals m times a, but a is really v squared over r. So if you do a little bit of algebra, you can get it down to this. Okay, and so now once you got it down to this, then you come, oops, sorry. Okay, so now you've got it down to that. Then you come over here and you do what we just did a minute ago. You get this, and then if you put them all together, then okay. So over here we've got what we got from this slide, and this is what we got from the other slide. So now all we have to do is put them together and do a little bit of algebra. And so what we get is this down at the bottom here. So the radius of any orbital is going to be the n number for that particular orbital squared, where n is some positive integer. Okay, so whatever the n number for that particular orbital is squared times Planck's constant squared, and then divided by k q squared times the mass of the electron times 4 pi squared. That'll tell you the radius. And so this, I think, is fully doable by everybody in the class. There's no calculus involved, no tricky stuff. So this is fair game to put on the test. Yeah, it's a lot of work, but that's okay. I mean, this is an honors class. You guys can do a lot of work. All righty. Okay, so now we got 15 minutes left and only one problem to go. So, okay, this problem here, number 20, was clearly the hardest problem on the test. Not because of the physics, I think. It's hard because of the mathematics, but I can think of 3 ways to do this problem. 3 different ways. And so let's talk through them. So first we have to settle up. So we do have to do the physics first. Okay, so we know that the work that's done by the electron gun is Q times V, and we know that that's equal to kinetic energy because, as I talked about just a few minutes earlier, you know the voltage is work over charge. Okay, you need to know this for sure, that QV is equal to kinetic energy. Okay, you need to know that. Now the problem is that the mass of the electron is not just m anymore, it's actually m divided by gamma. That's what makes it a little bit difficult. All right, so we know that QV is going to equal 1/2 times m over gamma times v squared. Okay, so all we have to do then is just solve for v. And when I say v, I mean velocity, not capital V, because we know the voltage. So be careful, don't get capital V and lowercase v mixed up. Capital V is the voltage, we know that. So lowercase v is the thing that we need. Okay, so this is the last time you guys are going to hear me say this, so savor it. From this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Okay, that's the last time you're going to hear me say that. Okay, all right, so all we have to do is solve for V. Now, like I said, I can think of 3 ways to solve for V. Before I do it, I'd like you to suggest a way. Though I hope that some of you did this. Tell me, what method did you use to solve for V? And I'm not going to move on until somebody types something into the text box, into the chat box here. Somebody tell me the method that you used to solve it. Google. I don't think Google's going to have this particular one. Google's got a lot of stuff in there, but I don't think it's going to tell you how fast the electron will be moving if it's got 5 megavolts on it. Try again. Come on, somebody here. I can think of 3 ways. You guys should be able to think of at least one. Graph it. Good for you. Dean, yes. Okay. So now this is kind of a messy problem because you got a V squared up on top and you got a V down in the bottom there. So yeah, Dean is suggesting that let's just put it into our calculator. And remember, we know how to solve complicated problems, right? If we can get it down to one equation, one unknown, we can stick it in the calculator, graph it, and look to see where now we have to get it to equal 0 first, okay? But so if we rearrange the equation, get it to equal 0, stick it in the calculator, graph it, it'll do it, okay? Now, that would work. Although, to be honest, when you got numbers this big, sometimes the calculator has trouble dealing with the numbers this big. And so here is a case where because of limitations with your calculator, you might run into some problems if you do it that way. Okay, but that is one way. Okay, now I'm going to do it a different way. And the reason I'm going to do it, well, one reason I'm going to do it a different way is because all year long I've been dissing Mr. Jensen. And so I feel bad about all the bad things I've said about Mr. Jensen. And, well, about the one thing that I've said so multiple times about Mr. Jensen. So to soothe my conscience here, I'm going to solve this step by step the way that Mr. Jensen would solve it. Okay. So what I'm going to do is I'm going to multiply it, or I'm going to rearrange it here. Okay, so I'm going to get that gamma up on top. So I'm multiplying both sides by gamma, and also I'm multiplying both sides by 2. So you up into this form. And then I want to get rid of that square root function. So I'm going to square both sides. So I'm left with 4q squared v squared times gamma without the square root times m squared v to the 4th. Okay, now what would Mr. Jensen do next? Well, he would probably rearrange it like, well, first thing he'd do is he would distribute this out. He would take the 4q squared v squared times 1, and then he would take 4q squared v squared times negative v squared over c squared, okay? And then he would probably rearrange it into this form right here. And you say to yourself, well, why would Mr. Jensen do that? Because it starts to look an awful lot like the quadratic equation. Now, it's not a quadratic equation, it's a quartic equation, okay? So that it's v to the 4th. But if you've got a v to the 4th here and a v squared here, maybe we can do some substitution. So some of you've heard the term U substitution, right? So this would be a great time to do a U substitution. I'm going to call it an X substitution. So what I'm going to do is I'm going to say wherever I have v squared there, I'm going to replace that with X. So v to the 4th is then actually X squared. So now I have a quadratic equation. And we know how to solve quadratic equations, okay? So Josh is saying, ew, Yeah, it's a lot of work, but hey, it'll make your math teacher proud, right? Okay, so we've got a quadratic equation where the a part of our equation is negative m squared. The b part of our equation is negative 4q squared v squared over c squared. And then the c part of our equation is 4q squared v squared. And so now all we'd have to do is stick it in our calculators. You guys do still have the quadratic formula programmed into your calculator, I hope. Okay. All right, so when I do this, so I get these numbers for my a, b, and my c. I stick it in a quadrat, and I get two numbers, one of which is negative, so I ignore the negative. I just take the positive one, and then I say, okay, but this number that we see right here, that number is not v, that number is x, okay? And x is actually v squared. So I have to take the square root of this number, and I get this number right here, okay? And so if I had asked for the answer in meters per second, that would be our answer. But I didn't ask for it in meters per second, I asked it in a percentage of c. So if I go and divide it by c, so what I get is that this was 99.87% of c. Okay. So yeah, it was a lot of work, but it'll make your math teacher proud. Okay. All right, so now we know two ways to solve this problem. I told you there was a third. Milo is suggesting that we use the solve function on the TI-89. Okay, yeah, I guess I would count that one. So then let's say it's 4. Okay, but Milo, actually, when you use the solve function on your TI-89, or actually your NSpires have a solve function too. What your NSpire is actually doing is solving it graphically. I mean, that's really what it's doing. It's just not showing you what it's doing. Okay, so there is one other method that I want you guys to use. Remember on the wall in my classroom, I've got up high on the wall, I've got all of those different ways of problem solving strategies. Remember those? Do you remember the one problem solving strategy that's not Mr. H's favorite, but hey, it works at least sometimes? Remember that one? Guess and check. Okay. Yes, good, Josh, you got it right. Guess and check. Well, here is an example where guess and check actually is a pretty good way to solve this problem. So let's solve it, guess and check. Okay, so we've got this equation right here. We've got, now in this case, what I've done is I've rearranged it so that I've got voltage all by itself on the left side. And everything else is over here on the right side. Now we don't know what the V's are. That's what we're trying to solve for, but that's okay. What we'll do is we'll guess a V. We'll stick it into this equation, and we'll see if the voltage, when I say guess a V, I mean guess the velocity. It's a shame that we got capital V and lowercase v. I understand that can be confusing. So what we're going to do is we're going to guess a velocity. I'm going to stick it into this equation and see what V comes out. And if the V is too big, then we know we need a smaller velocity. And if the voltage is too small, we know we need a bigger velocity. So you can see the first time around, what I did was I guessed 99% of C, because I knew it was going to be close to C, right? So I figured, okay, let's guess 99% of C. So I stick that in and I get a voltage of about 1.8 megavolts, which is too low, because I know it's supposed to be 5 megavolts, right? Okay, so I know that the velocity I put in there is too low. No problem, I'll put in a bigger velocity. So I go back, and this time I put in 99.9% of C. So when I put that into the equation, the voltage that I get out now is too high. Okay, it's 5.7 megavolts when it should have been 5 megavolts. So this is good because now I have it boxed in. Okay, I know that it's somewhere between 99% and a 99.9. I know the limits of what it is. Now I just need to work through there to find out exactly where it is. So my next guess was 99.7, which was too low. My next guess after that was 99.8, which was also too low. Okay, so now I know it's somewhere between 99.8 and 99.9. So now I've got it down to 3 sig figs. So if all I wanted was 3 sig figs, I could probably stop here, but okay, let's go on more, because I did want 4 sig figs. Okay, so I'm going to guess 99.85. Again, that turns out to be too low. So I do 99.88 That one turns out to be too high, but I'm really getting zeroed in now. And so my last guess here is 99.87, and that gives me a voltage that is right on the money. So bingo, I have got the game. So Yasna is saying it's time consuming. Yeah, I admit it's time consuming. But hey, at least it solved the problem, right?
Mr. Hendricks, I have
Yeah.
a question.
Uh-huh.
For the final one, guess of 99.88, it says that the velocity is below 5
Uh-oh.
times 10 to the 6th, but that's
Yeah.
just too high. I'm confused. Is that just a mistake?
Oh yeah, that's a typo, because look, I've got the same number for 99.85 as I do for 99.88. Okay, so good, thank you for pointing it out. Okay, so this number right here is a typo. I'm sorry, okay, I didn't do the math wrong. I just didn't type it in wrong. Yeah, so if you were to put in this number, okay, the number that appeared on my calculator was a number that was too high, and it wasn't this one. So sorry for that mistake. So tell you what, for the final time, right? Seeing as how this is the last time you guys are ever going to see me, if this is probably the best way for you to remember me is with the wig. I deserved it. Okay, so I apologize for the typo. Good catch there, Josh. Okay, so you see we got the three methods that we could solve it with. Any one of the three would have been fine. Okay, and all of these are methods that you guys could do. There's no calculus involved. There's no trig identities involved. We didn't take logarithms or anything like that. This is all math that every single one of you in this class could conceivably do. Okay, well, that was perfect timing. I see we got about 3 minutes left, and I'm done. So before I end the class, are there any questions about anything? Okay, so you understand when the test is going to be done and how the test is going to run. Secret word? Yeah, I suppose. Okay, what would you recommend? Oh yeah, Joseph, yes, I have definitely had a good year. I hope you guys have. This teaching from home thing has been a little weird, but okay, so secret word. Josh, you're the one that suggested it. What would you like it to be? Bye-bye? Okay. All right, I'll go along with that. All right, the secret word for today, the secret phrase is bye-bye. Okay. So I guess I will not see you guys again until next year, those of you that are graduating. I am going to be at the graduation. You guys know the graduation is going to be online. So even those of you that are not seniors, you will be able to watch the graduation if you want. Those of you that are seniors, you know there's going to be a drive-through graduation. It's going to be a little weird. I will be there at graduation. I won't be able to shake your hand probably, but I'll be there. Okay, so countdown to end the class here. Going once, going twice. Okay, I'm going to end the recording.